All right then. All right. So it's a pleasure to be back again for my final talk in this series of lectures. And the topic today is going to be about neutrinos in dense matter. And I'm going to talk about this famous thing, the Urca process, that's been around for a while, but I'm going to propose an improved way of doing it. So let's talk about that. It's based on this paper. So yeah, the outline is very simple. I'll give an introduction to what Urca processes are. I'll talk about the standard way of approaching them in terms of two contributions called direct Urca and modified Urca. And then I'll talk about why modified Urca in particular is not a great thing. And I'll propose a better way of handling the relevant physics called the nucleon width approximation. So, okay, let's orient ourselves. Here we're talking about ordinary nuclear matter, the standard nuclear matter fluid with neutrons, protons, and electrons, mostly neutrons, a few protons, an equal number of electrons to be electrically neutral, neutrinos, which may or may not be thermally equilibrated, or the other three are thermally equilibrated. And so it's described by these parameters. Tell me the density, tell me the temperature, tell me the proton fraction, and if the neutrinos are trapped in there, then also tell me the lepton fraction, and that tells me what this fluid element consists of. That's the relevant statistical mechanical information about this fluid element. So if we want to visualize what's going on, we remember that the neutrons and protons and electrons are always in thermal equilibrium, because they feel sufficiently strong interactions to ensure that in a very short time scale, they thermalize to a Fermi-Dirac distribution. The neutrinos, however, have a much longer mean-free path, so they are not always going to be thermally equilibrated. And what we're going to be talking about is these processes that establish this equilibrium between the species. But what we should imagine when we're thinking about one of these fluid elements is Fermi spheres of states that are filled up to a Fermi energy or a Fermi momentum. So here it's mostly neutrons, so we have a big Fermi C. This is in momentum space with a large Fermi momentum, a proton Fermi C with a smaller Fermi momentum, an electron Fermi C, and a neutrino Fermi C, which may or may not be thermalized, so I've drawn it with this funny shading. And you see that there's a little bit of blurring at these surfaces here, and that's because of the temperature. The temperature blurs out the Fermi surface, so there are some occupied states above and some holes below the Fermi surface. And the amount of blurring just depends on the temperature. And if the temperature is much less than the Fermi energy, then the blurring is a small fraction of the whole Fermi momentum. And so you can visualize it as this sort of filled ball of states. And the processes that we're talking about, these Urca processes, are dominated by modes near the Fermi surface, and we'll talk about that more as we go along. Okay, so what is this Urca process? I've mentioned it a few times, but let's say explicitly what it is. Here's a typical example of an Urca process. It's these processes here, if you want the whole listing. Here's an example. It's something where, for example, a proton and an electron combine together, they exchange a W boson, and change into a neutron and a neutrino. And you can also have the backwards version of this. You can move particles from the initial state to the final state. So this is neutron decay. That's an Urca process, or the reverse. These are all Urca processes. And so it's a weak interaction mainly, with possible strong interaction going on between involving the proton and the neutron here. So, okay, that's an Urca process. It's a process where the identity of particles changes. Only the weak interaction can do that, right? The electromagnetism can't change the identity of a particle. Strong interaction can't change the identity of a particle. So the weak interaction is the only interaction that can do this. And so it plays an important role in some things. For example, how the proton fraction relaxes to its equilibrium value is through processes like this, because these processes can change the number of protons. And that leads to bulk viscosity and damping, as I discussed in the last talk. Neutrino absorption opacity. This is also the process by which a neutrino gets absorbed. So if you want to know what's the mean free path for neutrinos to be absorbed, you're calculating Urca process rates. If the neutrino mean free path is short, so the neutrinos form an equilibrated fluid, then this process tells you how quickly the lepton fraction relaxes, and it also may tell you about shear viscosity, which is going to arise from neutrinos traveling from place to place and carrying momentum. If the neutrino mean free path is long, the neutrinos just stream out, and then this sort of process here is telling you about the emissivity of neutrinos, how neutrinos cool the system by carrying energy away. So there are many processes where Urca is essential. And where are they relevant? I think you can already tell where that's going to be. Supernovas, where the neutrino opacity is important, how far can the neutrinos travel? The quote deleptonization, where matter with the neutron-proton balance that we're familiar with in nuclei turns into neutron matter. The cooling of neutron stars, neutrino emissivity is relevant to that, and neutron star mergers, where the capturing of neutrino and the relaxation of the proton fraction are important features. So there's all sorts of places where you want to calculate these Urca processes and get the answer right.
Excuse me, I have a naive question. So you mentioned the mean free path, but like the mean free path is like calculated using sort of like kinetic equation or something like that. And when calculating that, you have to assume that whether like the neutrinos follow the like Fermi-Dirac distribution or not, but that also depends on whether the neutrino mean free path is short or not. So does that like require some sort of like self-consistent, I don't know, treatment, or is it
No, so if you want to calculate the neutrino opacity, then you don't
yes.
need to know anything about the neutrino population. You're
Okay.
just saying, if you give me a neutrino, how far will it go before it's absorbed? And that's independent of how many other neutrinos there are around the place.
I
Right?
see.
That's
I
an
see.
independent
Yeah.
thing.
Okay.
If I remember, I'll highlight a place where that comes up later on.
Okay. Okay. Thank you.
Yeah, you can calculate the neutrino opacity independent of everything else to do with neutrinos. Okay, so some examples here. So this is a simulation of a merger that was done a few years ago, and it was done with Urca processes and without. Without is gray dots here, which is measuring the electron fraction or the proton fraction up the side here, and the density along the bottom. But I'm not going to go through it in detail. The point is the gray dots are the fluid elements without putting in Urca processes, and the green dots here are the fluid elements with Urca processes. And the point is just that the distributions look quite different. Same here with a different equation of state. Okay, so your fluid elements will look quite different in terms of their electron fraction as a function of density if you include Urca processes versus if you leave them out. And another example, this is just motivation, right? I'm not asking you to understand these plots in detail. So here's another example where people calculated how much mass is ejected in a merger of two neutron stars, and depending on the viscosity, which itself is driven by these Urca processes, depending on the viscosity, more or less mass got ejected. And as you know, the ejected mass is how you get nucleosynthesis, how we get heavy elements on Earth. So it's important to calculate it correctly. So these are just examples of where this becomes important. So, okay, let's get to talking about the actual calculation. We're going to go under the hood now. We're going to actually see how to calculate these rates. So how do you calculate the rate for a process like this? A proton and an electron turn into a neutron and a neutrino. Well, the first thing you do is what's called the direct Urca calculation. And the direct Urca calculation is where you only include the strong interactions via the effects on the nucleon dispersion relation. The nucleon has some in-medium mass and some in-medium energy shift. You take those into account, which affect the dispersion relations of these ingoing and outgoing legs of the diagram. But other than that, you don't pay any attention to strong interactions. And then the rate calculation looks like this. So I'll just break it down because it's not too complicated. It's a field theory calculation. So there's a matrix element here, which comes from applying the Feynman rules using the standard model Lagrangian. Just W exchange between two particles. And so you get a matrix element here, which is just a bunch of dot products of these four momenta, right? The four momenta of the neutron, the proton, the electron, and the neutrino. And actually, in this case, they're all on shells. So all you need to know is they're three momenta. So you've got this thing, which is a function of the momenta of the particles involved. You've got an energy momentum conserving delta function that says the energy and momentum coming in has to equal the energy and momentum going out. And then you've got an integral saying we're going to add up all possible energies of protons and electrons coming in with Fermi-Dirac functions that tell us what's the probability that there is a proton with that momentum, what's the probability there is an electron with that momentum available to participate in this process. And you integrate over all outgoing neutron and neutrino momenta with Fermi-Dirac functions here telling you what's the probability there's a hole, an unoccupied state available to receive that final state particle. So, okay, that's all there is to it. It's this momentum integral with Fermi-Dirac functions to tell you how many are there available particles or holes, energy conservation, and a matrix element. And you just need to do this integral over all these 4 3 momenta. Okay, so you can do it, and actually you can make some good choices. Choose a frame of reference and things like that, and you can reduce this to a 4-dimensional integral. So it's not even as bad as it looks. You can reduce it to a 4-dimensional integral, and at low temperatures you can reduce it to an analytic expression because all the particles that participate will be on their Fermi surfaces. So you can even reduce it to the point where it's an analytic result at low temperatures. So that's the direct Urca rate. So it's a very straightforward calculation. People have done it many times. Okay, now what's next? Well, we expect strong interaction corrections, right? And the simplest standard approach is to include one correction called modified Urca. So here's direct Urca that we just did, this 4-dimensional integral. Here's modified Urca. Now, what's modified Urca? It's direct Urca, but it's where either the outgoing or the incoming neutron or proton has a collision with one of the spectator nucleons, neutrons or protons, that are just sitting around otherwise doing nothing, watching. But in modified Urca, there's a strong interaction between one of the participating nucleons and a spectator nucleon. So that's fine, but this means you've got more particles taking part, right? You've got 6 instead of 4, and that gives you more momentum integrals to do. And it turns out that this one, the best you can do is make it into an 11-dimensional integral. So that's a lot worse. But again, if you're dealing with a very low temperature, you can make the low temperature approximation and particles on their Fermi surfaces, and that helps you do this integral. Now, why is modified Urca maybe not so good? Well, one thing is that you need to do the Fermi surface approximation, and the standard way of evaluating is, you notice we had this internal line here. Unlike direct Urca, where all the lines are external, it's just a pure interaction here. In modified Urca, when this proton turns into a neutron, at first it's an internal neutron until it does its strong interaction with a spectator, and then it becomes the final state neutron. So there's an internal neutron line in this diagram, there's an internal proton line in this diagram. Now you know what to do. You've done field theory, right? You know what to do with an internal line. You put in the propagator, right? That's what goes in. But that's not what people do. They replace it with a number, right? 1 over the electron chemical potential is the number they replace it with. Okay, so why would you do that? Because it's simple, but obviously not very accurate. Okay, supposing you try to improve on that. Let's put in a propagator for that. Then, as we'll see in a second, these diagrams then diverge. And it's difficult to generalize this. If you want to do anything else, at low temperatures, you can handle it. But if suppose you want to do it at high temperatures, like in a merger, where you're not dealing with low temperatures, suppose you want to have a high temperature, then you have to do this integral. If you want to do something else, like put it in a magnetic field, we think there are strong magnetic fields in neutron stars. Again, you have to do this 11-dimensional momentum integral now in a magnetic field. So it's really quite hard to deal with. So let's think about, why do you need it? Can we ignore modified Urca? Can we just do direct Urca? Well, unfortunately not. There are some situations where that strong interaction correction, that collision with a spectator, is essential. So here, let's look at Urca rates, which could be we're interested in the neutrino opacity, emissivity, proton fraction relaxation, whatever it is. Let's look at the Urca rate as a function of the density. And what you find, depending on the equation of state, as it says at the bottom here, is that in some equations of state, there's a threshold density where direct Urca suddenly drops to a very, very small rate. And then below this direct Urca threshold, if you calculate that very bad approximation to modified Urca, no propagator modified Urca, then you get something that is actually the dominant contribution. So if you have an equation of state with a direct Urca threshold, and you want to calculate those Urca rates for whatever reason at densities below the direct Urca threshold density, you have to do some sort of correction to direct Urca, and the standard one to do is this modified Urca, where you neglect the propagator inside. Now, why is there a direct Urca threshold? Maybe some of you know this, but let me just quickly summarize why is there a direct Urca threshold. So you can imagine these Fermi surfaces here. We showed them before. And if the proton fraction is reasonably high, so there's a fairly good number of protons. I've shown this here with the concentric Fermi surfaces. So the neutrons are this blue Fermi surface here. The protons and electrons have the same Fermi momentum because, remember, they have the same density to ensure that things are electrically neutral. So if you want to do this process, proton and electron goes to neutron and neutrino, what have you got to do? Well, you've got to conserve energy, and particles on their Fermi surface can turn into other particles on their Fermi surface, conserving the energy. So a proton and an electron on their Fermi surface have enough energy to turn into a neutron on its Fermi surface and emit a low energy neutrino. And in this case, you can conserve momentum as well, because if you take a proton on its Fermi surface with this momentum, an electron on its Fermi surface with this momentum, and a proton on its Fermi surface with this momentum, you add them up, and you get a momentum that lies on the neutron Fermi surface. So you can indeed make a neutron on its Fermi surface from a proton on its Fermi surface and an electron on its Fermi surface. The momenta and the energies all add up, and you can do the process. However, supposing that the proton fraction is lower, there aren't so many protons around, so now a smaller proton Fermi surface, we still want, in terms of energy, an electron and a proton on their Fermi surfaces have enough energy to make a neutron on its Fermi surface. But in this case, they don't have enough momentum. If you take them, even if you line them up as much as you can, so there's no cancellation, the momentum of an electron on its Fermi surface combined with the momentum of a proton on its Fermi surface is not enough to make a neutron on its Fermi surface. It's only enough to make this amount here, which is an already occupied state. You can't put a neutron there. And anyway, we don't have enough energy because the energies don't add up. So if the proton fraction is low, that's when that killing off of direct Urca happens. It's when the proton fraction is too low, the proton and electron Fermi momenta are not big enough to allow the proton and electron to participate in this process. It's kinematically forbidden. You can't conserve energy and momentum. So now that the direct Urca process is not happening, and you have to go to some alternative like a strong interaction correction. Now, this threshold, this sudden cutting off of direct Urca, is softened by various things. One of them is thermal blurring. Remember, as you turn up the temperature, these Fermi surfaces get blurred, and then you have a contribution, but it's suppressed by e to the minus some energy over temperature, right? The Fermi Dirac is slightly blurred, but it dies off very quickly. And the other thing that we'll talk about, which will become our central player, that also blurs these Fermi surfaces, is the nucleon width, and that's going to be the central player in what we talk about later on.
Let me the simple question. The contribution of the neutrino Fermi momenta is neglected since usually most of people consider the low temperature, for example, cooling. But
Right.
The contribution of neutrino momenta could not be neglected in high temperature region or not.
Right.
I think
Yes. So then this complicated this.
it is another effect of that.
Yes. So what this is in this description I gave is valid in cool or cold nuclear matter, where you, as you say, you can neglect the neutrino energy and momentum. But yes, exactly right. This thermal blurring that I talked about includes also, I didn't say it explicitly, but you drawing it out, which is quite right. It also includes the taking into account the energy and momentum of the neutrino. Yes. Good point. Okay. Any other question at this stage?
What if there's like a short range correlation that modifies the like Fermi-Dirac distribution or something like that?
Well, I think in some way, okay, I think the nucleon width is kind of that. Okay, it's the part of that that contributes. But let's hold on to that thought and let's see as we go along if this looks right to you. So yes, I said different equations of state have different direct Urca thresholds. So here's some examples. This is that momentum deficit. So when it's positive, direct Urca is forbidden. When it's negative down here, direct Urca is allowed. And these curves are for different equations of state, some pretty standard, well-known ones. So you see here that the NL3 equation of state, direct Urca is unable to happen until you reach a density of just above nuclear saturation density here. But for TMA, it kicks in at about twice saturation density. For APR here, the black line, it kicks in at just about 5 times saturation density. For DD2 here, it never kicks in, right? So the direct Urca threshold is very variable between equations of state, and you can't say that we don't need below threshold rates, right? Yeah, depending on your equation of state, you may well need below threshold rates. So yeah, so this is that picture, right, where here's an equation of state with the direct Urca threshold. When you go below that density, the direct Urca rate drops off very dramatically because there's only the thermal blurring taken into account here. And then that no propagator modified Urca is the dominant contribution. And you see this very dramatically in cooling. Again, I'm not going to ask you to understand this plot, but here they've got cooling. This is temperature as a function of age for neutron stars. And these lines here track how stars cool if they've got modified Urca, and these stars track how they cool if they've got direct Urca going. And there's a huge difference. And obviously, you can't neglect whatever the physics is that's giving you modified Urca here. It's important. But I've just argued that this no propagator modified Urca, that evaluating those diagrams and pretending that that internal line propagator is just a number, that's clearly not a good approximation, right? If you did that in your field theory class, or your students did that in your field theory class, you know, there'd be points taken off for pretending the propagator is a constant. So can we do better? Can we improve on the standard approach to the modified Urca contribution? So people have done this, try including the propagator. And what happens if they do that? Well, in this same diagram here, increasing density here, Urca rate here, they include the propagator, they get a faster rate, but then when they reach the direct Urca threshold, the rate diverges, goes to infinity. Here's the actual plot from the paper by Stern, Baldo, and Hansel, and these red lines show their rate diverging. They also show that the no propagator modified Urca, even far below threshold, is wrong by about a factor of 10. Okay, so there you go. So it's wrong by a factor of 10 where it isn't divergent, and then it diverges at the threshold. So it's really not good. Okay, and why is it diverging? Well, we can see why if we go back to here, because when you go above threshold, this process can happen, right? So that means a proton can turn into an on-shell neutron. So when you calculate your modified Urca, you find that sometimes your proton turns into an on-shell neutron. Well, the propagator for an on-shell neutron is infinity, right? Because the propagator is 1 over the deviation from being on shell, right? On shell is where the propagator has a pole. So naturally, these diagrams here are going to diverge when the internal line goes on shell, and the internal line will go on shell when you're in a regime where direct Urca can contribute, maybe due to thermal blurring for whatever reason. And so that's why you get this very unpleasant behavior that you include the propagator thinking you're doing a good thing and improving the calculation, and you get punished with a horrible divergence. So obviously there's something wrong with doing that, right? Obviously that's not the right way to handle this strong interaction correction. The physics is there, but how do we handle it correctly? So let's think about what is the modified Urca trying to do so that we can do it better. Well, you can think of that collision with a spectator nucleon. You can think of it this way. You can take that incoming spectator nucleon and fold it over into the final state instead. And you can think of the modified Urca process as creating a particle-hole pair near the Fermi surface, right? And you can understand this fairly easily, that what happened is you collided with a nucleon somewhere near its Fermi surface and created a hole, right? You knocked it out of that state, you gave it some momentum, and you knocked it across to another state, okay, which wasn't occupied. So you created this whole particle pair. Creating a whole particle pair is the same as moving a particle from one place to another, right? That they're just different words for the same thing. So this is still the same process, but it gives us a different way of thinking about what this process means. So what does this mean? If you created a neutron, and then through a strong interaction, it can be a neutron, but also spit out a particle-antiparticle or particle-hole pair. Well, what that tells us is that when we're in a dense medium, where there's lots of states available at the Fermi surface where we can make particle-hole pairs, this nucleon is actually unstable, right? This is a decay, right? This nucleon here decayed into a nucleon plus a particle-hole pair. Okay, so that's a decay. And that means that actually the in-medium nucleon is unstable. Another way of saying that is it has a width, right? Unstable particles have a width. Or another way of saying that is that their energy has an imaginary part. So the physics behind this scattering off of a spectator is really related to the in-medium width of the nucleon. And that's the thing that we really ought to be thinking in terms of. So let's go forward trying to pursue this and obtain this strong interaction correction to this important Urca rate, thinking of it in terms of an in-medium correction, namely a width. So just to be clear about this, if you let the nucleon have a width, then you won't get a divergence, because this propagator, this thicker two-arrow propagator it's some 4x4 Dirac matrix on top. And on the bottom, you have E squared minus K squared minus M squared, right? But the mass now has an imaginary part. Okay, the particle has a width. If you didn't have this imaginary part here, then when E squared equals K squared plus M squared, this propagator would blow up. And that's the divergence that we saw when people put in that propagator, the naive zero width in medium propagator, they got a divergence. But if you include the width here, then this is not going to diverge. Even when E squared equals K squared plus M squared, this is not going to diverge. You've moved that pole off the real axis. So, okay, this is looking promising. We can put in widths for particles. But how exactly? Because these particles, this particle here, we've got an internal particle with a width. We've got these particles here, which are final state particles. In terms of field theory, what do we actually do to give one of these particles a width? So if you want to do this, the cleanest way is to use a formalism that goes by the name of Cutkosky. So I'm going to give you a very quick overview of how this Cutkosky formalism works. So the fundamental approach here is to say that the rate of some process is obtained from the imaginary part of the initial state self-energy. It's really the optical theorem for quantum fields. So how does this look in practice? Here's an example, a little different from what we're doing, but similar in spirit. Imagine some scalar particle here that decays into a fermion-antifermion pair. Okay, so if you wanted to know the rate, the lifetime of this particle, right? You want to know the rate at which that decay happens. You would calculate this. You'd take the initial state, look at the Feynman diagram that says it decays into a fermion-antifermion pair, square it to get a matrix element, and then sum it over all the final states that this particle can decay into, and that would be the rate. This theorem says that is actually equivalent to taking this diagram and doubling it in a mirror, right? Flipping it over here. So you've got the scalar particle decays into a fermion-antifermion pair, and then those reassemble themselves back into the initial state again. Okay, so this is a self-energy, initial state self-energy. You take the imaginary part of that diagram, and that is giving you this rate. Okay, that's the claim. Now, maybe you're familiar with this. If so, well done. If you're not, then at first sight, this looks extremely odd. This looks again like the kind of thing where you would punish a student and give them 2 out of 10. Because normally in quantum mechanics, we're very careful about distinguishing between amplitudes and probabilities or rates, right? You square the amplitude to get the rate. If you use an amplitude by mistake instead of a rate, you'll go horribly wrong. If you use a rate instead of an amplitude, you'll go horribly wrong. You've got to be very careful about this, right? Don't forget to square the amplitude to get the rate. But in this case, we've got a formula where we've got a rate, a probability on one side, and an amplitude, a raw unsquared Feynman diagram on the other side. And we're saying they're equal to each other, okay? So this is in some ways shocking. That where it comes from, here's a little micro derivation here, it comes from unitarity, that you can write the scattering matrix that tells you the probability for an initial state to evolve into a final state as the identity, nothing happens, plus I times a T matrix that tells you what non-trivial things happen. And then unitarity saying S squared equals 1. You plug this in and you get T squared terms, cross terms that are linear in T, and the identity. But the identity is on the other side as well, so that cancels. So this turns into a relationship between T squared and T, right? So you get a relationship between amplitude squared and amplitude. And it comes from this unitarity condition, which gives you this very odd-looking rate equals amplitude type equation. But it's quite straightforward once you know where it comes from. But okay, so we're interested in calculating these rates. And we're now going to think of it differently. We're going to think of ourselves as calculating the imaginary part of a self-energy. So in the case of what we're doing, let's think of it as a neutrino self-energy. So you can think of the process that we're studying as neutrino absorption. That's one of the ways in which you can understand an Urca process, right? So it doesn't matter, you can frame it different ways. But so if you think of it as neutrino absorption or neutrino destruction, then the neutrino comes in, turns into an electron and spits out a W, which turns into a proton and a neutron hole. And then we do that doubling over of back into the initial state again. And we say that the rate at which neutrons are being absorbed is the imaginary part of this diagram, this neutrino self-energy diagram. And that's equivalent to evaluating half of this diagram and integrating over all these final state momenta. Basically, what you've done is you're saying that here, the loop integral here, over all possible momenta in the loop, maps onto the integral over final states here. Okay, those are the same thing. So, okay, this has been done before. This gives us a way of doing, but this is just direct Urca, right? So this is now direct Urca reformulated using the Katkowski rules as an imaginary part of a self-energy calculation. But it's going to look very similar. Okay, in fact, it may even look the same. So, okay, that's direct Urca. Now, how is this formulation going to help us include widths? Well, so direct Urca, we just said, is the imaginary part of this diagram, where the nucleon, the neutron and proton in this internal loop here, they have real masses, right? So the propagator is just 1 over k / minus m, and the same for the proton. And we're neglecting other strong interaction corrections. We're just doing that, the in medium neutron and proton. So all we need to do, if we want to do include widths for the neutron and proton, is include widths in those propagators. So we just turn our thin propagators here into thick propagators here, where now when we evaluate this Feynman diagram, instead of for the propagator putting in 1 over k / minus m, we'll put in 1 over k / minus m with an imaginary part. Okay, and the same for the proton. So we just turned our thin, no width propagators into thick 2-arrow propagators with in medium widths. And that should give us a proper field theoretically valid way of making sure that we're evaluating this rate, taking into account the possibility that the in medium neutron and proton can scatter off spectators and create particle hole pairs. Okay, that will now be included if we've got the right widths in here. So, okay, any question at this point? This is what we're going to use from now. Okay. All right. Okay. Okay. So how do we implement a nucleon width? How do we evaluate that Feynman diagram with a propagator in? So I can write it down easily enough. It's 1 over k slash minus m, usual propagator, but with an imaginary part for the mass. But it's not entirely straightforward to evaluate Feynman diagrams with this in, because a lot of the technology that's been developed is based on Feynman propagators where you don't have an imaginary part and you assume the poles are sitting on the real axis, the real energy axis, and now the poles aren't on the real energy axis. So it's going to be a little bit of a pain. But one way of doing it that minimizes the amount of new calculation we have to do is to say this propagator with a width is actually equivalent to the propagator without a width, but where the mass is integrated over a range of values. So you can, this is just a simple identity here, that pushing that pole off the real axis, the real energy axis, is equivalent to saying this mass is not just the mass we thought it was, but we're going to integrate over propagators with that mass plus a range of values either side, weighted by this Bright-Wigner function, which is peaked where the sort of real part of the in-medium mass is, but now it has some width, and hence the name width, that says either side of it, there's some amplitude for the mass in this propagator to be bigger or smaller than the central mass by some amount, gamma or 2 gamma or something like that. So this Bright-Wigner function says, yeah, the mass is roughly big M here, but it can vary, and it's weighted according to this Bright-Wigner function. And the Bright-Wigner function is a simple function you can write down. And in the limit where the width goes to 0, this turns into a delta function, and then you're back to just propagators with no width and with a mass. And actually, when you did field theory, when you learned field theory, you probably learned it with an I epsilon prescription, right? And the I epsilon is basically just assuming an infinitesimal width. And we're taking that width and making it not infinitesimal. It's actually physical now, that the particle really has a width. So it's not an I epsilon prescription anymore. It's got an actual non-zero finite width, finite imaginary part there. So what that means, now it's actually very simple to implement this nucleon width, because since it's the original calculation with a real mass, but just smearing the real mass over some Bright-Wigner weighted range of values, we can now say, okay, here's our diagram with these propagators with widths in, but this propagator is just a mass smearing of the original neutron propagator, just having a range of masses dictated by this weighting function. For the proton, we do the same thing. The proton propagator is just a real mass proton propagator with an smearing it over a range of values. And so our nucleon width approximation, which is what I'm calling this, the nucleon width approximation Urca rate is just the original direct Urca rate, but where the mass of the neutron and the mass of the proton are now integrated over some range of values. Okay, you're just smearing them. So that's all that
May I ask you a question?
Yes.
This integrated small m, integrated value, range from 0 to infinity, or
No, minus infinity to infinity.
so why it can become negative?
Well, that is just what you have to do for this identification to hold, right? This is just a mathematical fact here, right? That a function in the complex plane, if you push the pole off the real axis, that's equivalent to, if you look on the real axis, that's equivalent to having a Bright-Wigner weighted function that extends off to plus and minus infinity. So it's just math.
Okay.
So this negative mass corresponds to the mass in high density region, because if we consider the effective mass, then this could be negative because of the interaction. For example, in the RMF model, it could be the sigma interaction. So this is correspondence.
Well, I mean, remember, this is math. I mean, in some sense, it's physics, but it's math, in the way we're implementing it, just saying that the collisions with spectators are equivalent to sometimes, occasionally, the particle can have a negative mass. I mean, it's to do with that. It's not, there's separate interactions that may shift the real part of the mass, the real, right? This is handling the imaginary part by smearing the real part. I think it's a little, it's separate physics from what makes the real part itself be bigger or smaller. But it means we have a very
sorry, excuse me. Sorry to interrupt. So the previous I mean the propagator in the previous slide. So is that like a lemma representation of the?
Yeah.
I mean, yeah.
Yeah.
That's
It's a spectral representation.
Right.
I mean,
right. Yes. Yes.
You can do these in different ways. You can do a spectral representation in terms of the energy or whatever.
Yeah.
Here we're doing it in terms of the mass.
Yes. Yes. So maybe the integration measure, I mean, can be dm squared or like.
Well, in this case,
that's the same thing. But
this is dm in this case.
yeah.
But,
Yes. Yeah.
Okay.
Okay. Yeah. Thank you.
There may be other ways of implementing this, but what's attractive about this way of doing it is that you don't have to redo your direct Urca calculations, right? You take your already existing direct Urca calculation, just generalize it so the mass of the neutron and the mass of the proton are parameters and not just fixed numbers. And then you have to introduce two extra integrals integrating over those parameters with these weighting functions. And your piece of code that gives you direct Urca, wrap it in this integral, and it now gives you the effect of in-medium widths, which is what modified Urca was trying to do. You'd still need some model of the strong interaction to estimate appropriate values for those widths, right? This is a recipe that needs to be told what those widths are. So I'll get to that in a second. But so you remember the reason we did this was we didn't like having a divergent rate here when we put the propagator into modified Urca. This fixes it. So this red line here is the nucleon width approximation, and you see, and this green dashed line here is direct Urca, which dies off at the direct Urca threshold. But the red line for the nucleon width approximation in the direct Urca allowed region tracks direct Urca, but then when you go below threshold, it starts capturing that collisional broadening, what people call modified Urca contribution. And below threshold here, it agrees quite well with the calculation that was done where people include a relativistic propagator in the modified Urca diagram. It actually agrees quite well with that below threshold here. And they all disagree with the traditional standard no propagator modified Urca. And this is using a width, which is very simple from Sidrakian and Deepering some years ago, who estimated that the nucleon width would go like t squared over t naught with some value for t naught here, and would be roughly independent of the density. Okay. Yes, it's a good moment to see if anybody wants to ask anything.
Can I ask? So this is, as far as I understand, so this is resumming the self energy into the like nucleon propagator, and you make the nucleon propagator dressed, right? Is that true?
Yes, it's a very specific piece of dressing, right?
Yes,
when you dress things, and in this case, it's dressing it with a width.
Yes.
Right. People already dressed it by shifting the real part of the mass. So there was an in-medium effective mass. They'd put in an in-medium effective energy shift before. Okay. But so this is just another piece of dressing.
Right. Yeah. I see. Yeah. So this is very natural idea. And yeah, this is
it's very natural. And it's, I think, what we should have been doing instead of modified Urca all along is my claim. Yeah.
Okay. Yeah. And my question is then, is that like constant width approximation good approximation? Is there like in any limit, like in the forward limit, would there be like this gamma should be like dependent on the frequency or something like that in the like lambda damping or something like that?
Okay, very good. Okay, very good question. So this width that I've written down here and that we use to get this red line here is simplified in various ways. One is that we assumed it didn't depend on the density. That's at a sort of macroscopic level of, at different densities, there's the same width. But within the given process, in principle, that width could depend on the energy and momentum of the nucleon itself, right? In that propagator, you could have a momentum and energy dependent width. So we've not done that, right? We've assumed it's, our approximation here is that the width is independent of the momentum and the energy of the nucleon. That's not necessarily true, and one could that would be a way of improving on this calculation.
I see.
Okay.
Yeah,
but we're taking steps here, and what I'm suggesting is this calculation is an improvement on modified Urca.
Yes,
I'm not
yeah,
saying
I
this
completely
calculation
agree.
is the final improvement. There's clearly room to make it a more sophisticated calculation.
Yes.
As I will, at the end, I'll have a list of things to do next. And
Okay, yeah, thank you.
Can I ask the practical aspects for neutron star Curie calculator?
Well,
because we did a superfluidity actually. Without superfluidity, then it is difficult to explain the sum of cold neutrons such as the Vela or something. So then in this case, maybe the thought is very natural to be extended. That is the combination of the modified Urca and the dielectric intensified framework. It's good, but how to include, for example, the pairing effect?
I agree. So yes. How do you include superfluidity? That's one of the you guys are doing very well because you're anticipating bullet points in my final transparency, final slide of things to do next. Okay, so these are all completely valid points. Okay. Anything else? Anybody else want to anticipate more pieces of my my upcoming slides? Okay. Right. So I'm trying to sell this, as you can tell. So what are its advantages? Here it is. It's very simple. It's just wrap the direct Urca in two mass integrals. Firstly, it agrees with the best previous calculations here. Below threshold, it agrees with this when you put in a relativistic propagator into modified Urca. Above threshold, it agrees with direct Urca. At threshold, it behaves smoothly and sensibly. It distills the strong interaction effects into these parameters, so you can then, just look at different models of the strong interaction, calculate different values for the widths, and put them into this calculation. It nicely sort of factorizes the calculation into bits that come from the strong interaction, which then contribute to a weak interaction matrix, weak interaction rate. It's easily generalized. Anything that you could do with direct Urca, you can now do and include the modified Urca effects. So, you can do direct Urca in magnetic fields. You can do direct Urca at high temperatures, just do the full phase space integral. All of those things you could do with direct Urca, you can now do those and capture the collisional broadening effect, whatever you want to call it, the modified Urca effect, the in-medium width effect. These are all different names for the same thing. It's not that bad to evaluate. We've added two integrals. So at low temperatures where you could reduce the direct Urca using the Fermi surface approximation to an analytic expression, it just becomes a 2D integral, these two mass integrals of that analytic expression. But even if you want to do it at higher temperatures where you can't reduce the direct Urca rate to an analytic expression, it's just those four momenta that you integrate over in direct Urca combined with these two mass integrals. It's a six-dimensional integral, and the integrand is pretty well behaved. It's a rate, so it's positive everywhere, and it's got a definite region of support, right? It doesn't have a little island somewhere where it's zero in between, and then there's some contribution somewhere else where it's non-zero. It's got a sort of compact, I don't know, I think it's mathematically not technically compact, but it's got a sort of a single region where the integrand needs to be evaluated, and it's always positive. So basically, it's very friendly to Monte Carlo, right? It's not oscillatory or anything like that. And it can be systematically improved, and we've already alluded to some of the ways in which you could systematically improve it, and I'll go on to say more about that. Let me just now say a quick word about how it captures the correct physics above and below threshold. So this is a diagram in that mass plane, okay? So this is, it's rather small here, the neutron mass along the bottom and the proton mass up the side here. And the orange shows you how big the contribution is. And so this left-hand one here is when you're above the direct Urca threshold. So these dashed red lines here show you the real part of the in-medium mass. And all that this nucleon width approximation does is introduce some blurring. So it blurs these masses a little bit around their real in-medium values. But since the direct Urca process is allowed for the real in-medium values, where the two red dashed lines cross, that's where if you didn't include widths, you just evaluate everything here, right? And you'd get the direct Urca rate. You'd have a delta function here for the masses. Now you don't have a delta function here. These Bright-Wigner functions smear it out a bit, but basically you've just got a smeared out version of what previously was a direct Urca, was a delta function, and so you're going to get about the same rate. Okay, it's just like a slight regularization of that delta function into a finite width distribution, but it's not very wide. You're at low temperature, and so you just get basically the same integral. Over here is what happens when you're below threshold. So this region here, that's partly blue and partly orange, is the kinematically allowed region. And now you're below threshold, so where the masses take on their real and medium values, where the dotted lines cross here, this is outside the kinematically allowed region. So the integrand is 0 here. It's forbidden by momentum conservation. But if you reduce the mass of the proton a bit, then the process becomes kinematically allowed, and then you're in the tail of one of these Bright-Wigner functions. And so now you get a somewhat reduced contribution. This is how we get the effect of modified Urca, okay? That you're finding that, yeah, the process isn't allowed if you neglect the widths, okay? That's the sharp death of direct Urca. But if you allow them to be a little bit wide, if you allow a little bit of width in the neutron and proton dispersion relations, you find that down in the tail of the Bright-Wigner, somewhat suppressed, but not 0, there are some masses for which direct Urca is now kinematically allowed. Changing the mass changes the Fermi momentum, changes those kinematic relations. And so you're capturing from the tail of the direct Urca in the proton mass and in the neutron mass, from the tail of the Bright-Wigner, from the tail of the Bright-Wigner in this integral over direct Urca rates, you're capturing a subleading contribution, which is all there is. And that's the effect of modified Urca. So it's the tails of Bright-Wigner functions is what modified Urca really is. Okay, so let me conclude, because it's about time for that. So my conclusion is Urca processes are important. We care about neutrino dynamics. We care about isospin equilibration in supernovas, in neutron star mergers, in cooling neutron stars. We have a simple recipe for doing a better job of capturing that modified Urca contribution, pretty much just using our existing technology for the direct Urca rate. It avoids that unphysical divergence. It's easy to explore different strong interaction models. It's easy to generalize. I said these things before. It's easy to evaluate. It can be systematically improved. Okay, I think I already said all these things. So let me go to the next steps things. So this is the final slide. So there are lots of ways, as has become clear from the questions, there are lots of ways in which you can take this further. So in the calculation I showed you, we were not actually consistent. We used Sidrakian and Deeperink's calculation for the width, but we used the equation of state we used was a different equation of state, not the one they used. So you should really do a consistent nucleon width approximation Urca rate calculation using something consistent. And chiral effective theory is a good example, because in chiral effective theory, you can calculate the width and you can also calculate the equation of state. So you can do the whole thing in a consistent single framework. You could revisit existing calculations that use modified Urca, such as cooling of neutron stars, neutrino opacities, and those, and redo them with this technology, with this nucleon width approximation. You could explore generalizations, like it's been very difficult up to now to calculate a modified Urca rate, including a magnetic field. I don't think people have been able to do it other than in the low temperature regime where you can approximate it. And even then, you're probably doing it wrong because you're treating the internal propagator wrong. Now you can do a proper job. Now to some more significant things, okay? When I say significant, I mean more challenging is what I should say. One thing is we completely neglected vertex corrections, right? All we did was correct those propagator lines in that diagram. We didn't correct the vertices. So you could also start thinking about strong interaction corrections to the vertices where pions get exchanged between the neutron and the proton. As people already brought out by questions, even if you're just sticking to the nucleon self-energy, you could do a more complete job with that. You could allow momentum and energy dependence, and you could also possibly look at different Dirac structures. Like, okay, there's one that looks like a round singlet. The mass has a width, but maybe you could have other imaginary components in the propagator. Superfluidity, which was just mentioned, is here. You could do the same thing, but use Nambu-Gorkov propagators, which are the things you use when you have a superfluid and particles can turn into antiparticles. You could do this calculation again, but this time with Nambu-Gorkov propagators, allowing for the possibility of superfluidity of the neutrons or the protons. And I should also mention that there's been a non-relativistic formulation. Ours was relativistic, but there's a non-relativistic formulation done by Armin last year, in which he was able to address some of these things. So, okay, that's the end. Thank you very much for your time.
Yes. So we accept the questions and the comments. So please unmute the mic if you have a question or comments. Yeah.
So may I ask, so although you didn't state in this way, but can you state that there is no such a thing as a modified Urca, but it's just a like immediate modification to the Urca process, like the ordinary?
Yeah, well, okay. So okay, let me skip. Maybe I can skip to one of my extra slides for this. Yeah. So okay. So really, what you should think of is this rate we're talking about is the imaginary part of this diagram. And we've got a neutron-proton loop here that's really a WW in medium correlator, right? It's really the current that couples to the W, that current correlator. This whole thing here has all the strong interaction corrections in it. So what we did was single out one of those, which is the imaginary width of these individual propagators. But you need to do that. You may need to include other single particle corrections in these propagators, and you would need to include vertex corrections, right? But if you include all those things, you're basically evaluating this current correlator in the medium, and then it's just this module that you plug into this diagram, and out comes the correct answer for in this case, the neutrino absorption rate. Okay, so that's the framework.
Okay, yeah, I see. Thank you.
Can you respect what cluster identity?
Can you respect
what cluster identity?
what okay, that's an excellent question. Okay, so right, so this is a current correlator, and normally when you do current correlators, you have to be concerned that this is a Green's function of currents, and if these currents are conserved, then there are Ward-Takahashi identities that the correlation function has to obey. And if we were talking about neutral current correlators here, where it was a neutrino, a Z boson or a Z boson here, coupling to a neutron in, neutron out, then that current is exactly conserved. That's basically the baryon number conservation current. And that current's exactly conserved, and that correlator has to obey a Ward-Takahashi identity. This correlator, however, is effectively an isospin correlator. This operator here turns a proton into a neutron, right? So that's the third component of isospin, right? It's an isospin correlator. Isospin is not an exact symmetry. In fact, not only is it broken by the neutron and proton mass difference and by electromagnetism, but in the medium that we're in, it's highly isospin asymmetric, right? If we're talking about neutron stars, you've got 95% neutrons, 5% protons. So already, even before you do anything sophisticated with this, if you just look at the in-medium mass corrections, they're different for the neutron and the proton, because the number of surrounding neutrons and protons is very different. So this current correlator that we're looking at, the current is sufficiently strongly broken. It's not obeying a symmetry that the Ward-Takahashi identity is, going to be violated considerably anyway, right? So I think that's not a worry, at least for the environment that we're doing it in for this purpose, which is this, as I said, very isospin asymmetric environment, and it's an isospin current. But I agree with you. Okay, so if you wanted to make sure, supposing you were doing a neutral current process with Z bosons here, and you wanted to make sure that that identity was respected, then as well, at the same time as doing in medium widths, you would at the same time have to do some of these vertex corrections so that together they gave you a correlator that obeyed the Ward-Takahashi identity. You would have to do that. I think we can get away without doing it in this case because it's so violated already. There's my long answer to your, but it's a good question, so it needs a long answer. I mean, you're welcome to ask more.
So, ask any questions or comments? So, yeah, actually, I can occur the many application for your topic. For example, maybe including context, actually when the electrical process occurs, then the cooling, rapid cooling occurs, and we can see. But this, how it is sensitive. That's how by changing the mass, then how the slow cooling track could be changed into the fast cooling curve. Maybe in your formulation, that this can give the exact variation of the mass. Maybe, previously most of people consider the sum of switch on and switch off, right?
Right.
But in such a case, sometimes it is sometimes not reliable. Yeah, many people say that the order of the variation of the mass is the order of 0.01 solar, 0.01 solar mass or something. But yeah, in your formulation, that maybe you can easily estimate. Maybe that may be very.
We can discuss. We can talk.
Yeah.
Be happy to try and
talk
about how that.
Okay. By the way, the one question is you show the mass neutron and the proton mass dependence on the contour.
Hang on.
Okay.
Was it this?
So in right panels case, is that in modified Urca regime, that is in right panels, is that agreement with the standard or formulation, that is in the standard formulation, the emissivity is proportional to the effective mass to 4.
Yes. So because the width goes like t squared. Okay. So that gets me to another of my extra slides here. So the direct Urca rate is t to the 5th. The modified Urca rate is t to the 7th.
Yes.
So NWA, it gives you t to the 5th when you're above threshold and t to the 7th when you're below threshold. And when you're at threshold, it gives you this in-between thing. Okay, so it captures the t to the 7th below threshold because the width goes like t squared, and the width is now responsible for the rate. So the width adds an extra power of t squared. So that's where that t squared comes from.
Okay.
So yes, we have the right powers of t.
Good. Okay. So are there any other questions or comments? Okay. If not, so then let's thank the
Thank you.
Mark for all of you.
Yes, it's a pleasure to be here and to be giving talk.
Yeah.
Yeah.
Thank you.
You included the corrections to the pole width, but any kind of transport, a big appearance or so on, for example, because this for me makes complete sense if you come from the QFT side, of course. So but I was wondering, of course, when you look at particles at finite temperature, what you see is, for example, not only the width, the pole width changes as you're trying to mimic, but there are also transport peaks appearing, right? For example, for thermal transport and
let's see. I don't think I know about this. So would this be transport peaks in an individual particle spectral function?
Yeah, people have computed for the sigma and so on. I know. I mean, I know for heavy ion conditions, I'm vaguely